what rate of change is that? Yeah,
What number is that?
Okay.
we'll talk about it. Don't stress about it right now.
Okay. So right here, you're gonna do option two.
See if you can figure out an equation based on what we've been doing.
And then right here, you're gonna do your other option.
What?
How's it going? For option one, I thought this was option one. So how much is
There's a way.
You start off with $0 on the first end. And then so we got equals. Click on that 0, and what happens is that just type in. Or no, not yet. Because you don't have a formula in there. How much is being added every day? So I take that 0 to B1 and I add 60,000 to it. Now, not 60,000. Remember, it's B1. It's at 0. But it's just like we did before. I hit equals. I have to click on what is previous to it. And then what are we doing to that previous value? Adding.
I just see the rate of change was 1.
Now you can drag and drop that power by 3. She's done. But that, does that adding 60,000? Or no, that's adding 1. We need to add 60,000 every day.
That's just.
Say again. Because so the idea is like he starts with $0, and then what's he getting every day? She literally had to see how he started out with $0, literally had 61. That's the idea. So I'm starting with that B1, what he has on 0 days. All right, how are we going now? How are we doing now? Making sense out of it? Why not? See if you can figure out which one's the better option. And then try to write an equation or something with it, okay? Celia, what do you think out of it? What about it?
Sorry.
Can you talk to your
They're really nasty.
I mean, they all have the stuff in the table, so they must have some idea what's going on. Talk with their group. What's going on? That's not mathematical language. What are you talking about? So what you're using is called a recursive formula, but like y'all are making this harder than it has to be. Option 1. How much does he start with option 1? Option 1. But so on day 0, how much money does he have? He hasn't worked yet, so he has $0. Enter.
60,000. And then X equals to 0.
And how did he get that 60,000? Don't just type 60,000. By working, but also because he started with how much? Right? So that's where we can type equals. Okay, well now it's B1, right? It's that previous value. And then what's happening to B1? Click back into here. For that column.
X is equal to 0.
No. And hit enter. So 0 plus 60,000 is 60,000. But because that's now an equation, right? You can just drag that through, right? Notice if you what's this one? Control. That's the shortcut on a computer for undo. But notice if I drag it down, we're gonna add 60,000 each time. So it just took the previous value. Like look right here in this formula. See how it says B2 plus 60,000, right? B3 plus 60,000. That's why we drag it and drop it. Yep. Yep. It is finicky sometimes, yeah.
Hey, sorry.
Is that the pattern that's happening? It's doubling every day? Okay. Yep. So tell me which one you think is better, see if you can come up with an equation from there. But we're going to get started in a second. Actually, hold on, let me finish this.
You know how to do this, right?
Does anybody need me to help them with the calculator part before we get started with the whole class discussion? Yes? Okay. Be right there.
I'm not a fan. Option B and C, but there's A and C.
No.
Exactly.
What did you do?
That's right. That's right.
Just made $1.
So you were able to do it with the 60,000? All you have to now know, so like remember, we were able to write this because we knew we were adding 60,000 every day. What's happening here every day?
Make that 0 because it's the first day.
What's happening in option 2? It's times 2, right? So I'm gonna come in here, equals, and I'm gonna click on that number, because that's what we're multiplying by 2. Okay, hit enter. I just put the equals, and it's that number that's being multiplied by 2, right? So that times 2 gives me that. Notice, if I click here, and I drag it down 1, then that means that you need to mess up something in the equation. But notice now, see how it says equals C2 times 2? So it's dragged down, but now it took that cell and multiplied by 2. And so now we need to keep that going all the way down to day 30.
I'm sorry if it didn't make sense because I suck at explaining stuff. It's not my thing except for explaining stuff.
Thank you. Thank you. So, it looks like we're getting these tables going. And I will say this, we're going to talk about a couple of things. But one of the main things I want you to understand is what you have been creating and using is called a recursive formula. What that means is if you go into option 1 to get this $1,680,000, what the calculator did is to get B29, it went to the previous B28 and did what to that previous number? Added 60,000. That's what a recursive formula is. It just goes to whatever happened before and then adds or subtracts or multiplies or divides to get the next number. And so if you can identify what the rate of change is, specifically, what's the rate of change here? Not just 60,000, it's doing what with that 60,000? Adding by 60,000, right? Because it was adding by 60,000 every day, you were able to write a formula for that. What was the formula that we wrote for option 2?
Formula? X equals point.
Sorry, no, like within the calculator, what did you do? You took the previous value and did what to it? Multiplied it by 2. Okay? And so someone was freaking out a little bit because they're like 2.68. Guys, if you highlight this cell, it'll give you the correct number. So like on day 28, Killua has 2684354. I'm just going to stop there. So he has $2,684,354.
Can you put arrow?
Huh? What'd you say?
Can you put arrow?
No. Then on day 29, 5368709. So on day 29, he has $5,368,709.
What job is he working?
That's what I'm saying. That's the job I want. All right, and then on day 30, $10,737,418. $737,418. So y'all tell me, which option you going with?
The second.
The second one, Key Anthony?
Is all of that in pennies?
No. That's converted to dollars.
So you take it today.
Because remember, and this is why we want to pay attention to how we started. What did we start with? 1 penny, which was $0.01. That's all dollars. Now, I want us to notice what we have found out is the rate of change. We have the rate of change of one of these is constantly what? What's option 1? What's that rate of change? By the way, this is where you want to flip the page over and write down extra notes. If you look on the back side, there's a part for extra notes there.
60,000.
It's not just 60,000, there's something more to it.
Adding 60,000.
Adding 60,000, we gotta be careful with that because it's going to matter in a second. Okay, so first rate of change. And we want to write it as constantly adding 60,000. And this is option 1. Option 2, what was the rate of change? Rate of change, was it just sometimes multiplying by 2 or was that a constant thing? Ah, so it's constantly multiplying by 2. Right, it's doubling every day. And so here's the most important part that's going to get us into the rest of the lesson. What were the 2 types of functions we were supposed to discover?
Linear and exponential.
Linear and exponential, yeah. And by the way, you may want to make a note to yourself, and if you don't have a table written down, I would. See table to make sense out of that rate of change. So which one of these is linear and which one is exponential?
Option
Linear
2.
is
Option 2
on-
is exponential.
I was, oh, no,
No?
never mind.
Well, I mean, if option 2 is exponential, then
It means that-
option 1 might be
Yeah.
linear. And this is a fundamental thing to understand. So Hudson, I mentioned one thing earlier, and I think this is how you do this. What did you notice, or what did y'all discover to realize, hey, option 2 is an exponential function?
You use an exponent for the amount of days. So when you use an exponent, it repeats the multiplication over and over again.
So let's look a little bit more closely at what you're talking about. So y'all ended up writing an expression to get to the final end there, right? What was the expression y'all wrote?
For option 2,
Yeah.
x equals 0.01 squared in parentheses and with an exponent of 30.
Was it
The
squared or
point, yeah, squared because you're multiplying by 2. I put that in parentheses and added an exponent in parentheses by 30.
And then what from there?
The exponent is 30.
Okay.
It's 30 days.
Like there? Did that give you,
No, the 2 is inside the parentheses. My bad.
the 2 is what?
Inside the parentheses because you're squaring the 0.01.
So like this?
No,
Square
you
it.
squared it and put it in.
I squared it.
You put it in the
I yeah, I guess that works.
Exponential.
You don't think that works? Okay, so we'll come back to this in a second. So type down your calculator. Tell us, does it get us that $10,737,000? I would just go to a calculator page. I would add a calculator page or scratch pad. Tori, you engaged in this conversation?
I mean, I'm confused a little. I get how he got that.
Oh, go over there, partner.
Sure did.
You sure about that?
What?
That's what I was supposed to
I got 1.0737. I thought I was
I need you to look again. Do we get the 10737? Sure. But that says E negative 51. That's scientific notation for 1.07 times 10 to the negative 51, which really means that I'm dividing by 10 51 times. Is that what we're supposed to have?
I got that.
So let's look at this one again. Okay? Peyton, I believe y'all came up with a different expression. What did y'all come up with?
Peyton?
You right there.
Peyton in group 7?
Right there.
Didn't y'all come up with something different?
Come on, how you know the paint is?
Yes, sir.
What did you come up with?
For option 2, we just came up with
Hello?
Here, Chris, that's cool.
What did you come up with?
for option 2, we came up with x equals 0.01 and x1 multiplied by 2.
Times. Say it one more time.
We did x1 multiplied by 2 and x equals 0.01.
That is not what I saw you have written down earlier. What I saw you have written down earlier was this.
Oh, yeah, we did do that.
Yeah.
We did that.
Oh.
Let's break this down. How much money does Killua start with in option 2?
A penny.
He started off with a penny, right?
Oh, true.
That's his starting value. What did he do to that penny every single day?
No, add 2. I mean, multiply by 2.
He multiplied by 2, right?
Yeah.
And what mathematical operation is going to show repeated multiplication?
Exponent.
An exponent. And how many times did he multiply by 2? 30 times. So let's look at this and let's consider this, okay? Check that. First I'll put that in the calculator. What do you get?
The negative 2 1 turns to equal E7.
So the decimal was here, right? So 1, 2, 3, 4, 5, 6. Oh yeah, that would be 7. Right? Now we'll also say this, if you get that scientific notation, if you scroll up until it's highlighted, until it's highlighted, and hit enter and bring it down, it'll get rid of the scientific notation. So what I'm referring to is 0.01 times 2 raised to the 30, because notice it's only the doubling that's getting happening 30 times. So if I scroll up and hit enter, notice that scientific notation goes away, because I've just brought that number down. That's the $10,737,418. Okay. So let's come back over to here. How would I write this as an equation for any day? How would I rewrite this to represent any day? And what I would point out is we need to figure out which things would stay exactly the same and which of these would be a variable. For instance, hold on one second, if I was looking at 27 days, not 30 days, would I still start off with a penny?
Yes, you would. No.
If I'm trying to get to the 27th day, figure out how much money he has on the 27th day, did he start off with a penny?
Yes.
So then what's going to stay the same? What's going to change? Jackson.
The exponent will change.
Exponent changes?
Exponent changes 27.
So then for 27 days it would look like this?
Yes.
So then what would the equation be for option 2?
0.01 multiplied by 2 with an exponent of x.
Would that represent how much money he has for any day?
Yes.
Kaya, you look like you have a question. Or are you just trying to wrap your brain around that? That one? What are your questions up to this
Explain
point?
a second.
This one right here?
Yeah.
Or this one? Okay, so please pay attention. Listen. What we want to notice is he's still starting out with a penny, right? No matter what day he's on, he starts out with a penny. That's the starting value. You could also talk about that as the y-intercept. And then what's happening to that 1 penny every single day? Is being multiplied by 2. And notice the exponent is just whatever day he's on. And so if the day he's on can change, we're going to have to use a variable. Does that make sense, Alicia?
Yeah.
Okay. Yes, Anthony.
Gabby wanted to know with F of X coming into play anywhere in there.
That's a good question. Okay?
She said F
Notice
of X.
X would be my input. I need something to be the output. What are the two options that we usually use for the output? Y equals, or a slightly better notation is F of X. The reason, and we're going to actually talk about this in the first lesson in the book, the reason why we use F of X is because that allows me to see my input of X and my output is the whole F of X. And we'll look at this a little bit more. But this is powerful. And I'm going to erase just a little bit up here. Actually, I'm going to erase this. Yeah. So, if I wanted to know how much Killua would have on day 11, notice I don't have to go, once I have an equation, I don't have to go through all that table and create the whole table. I want to know day what again? 11. What would that 11 get substituted in for? X. So with function notation, I can say f of 11. Notice how 11 is taking the place of x. That's the input. So now when I come over to my equation, what's going to take the place of x? 11. So f of 11 equals, can someone put that in our calculator, please? Say again.
20.48.
20.48. And so now because of my function notation using f of x, I know on, that's 11 what again? 11 days, that's my input. On day 11, Killua has made $20.48. Function notation is excellent for writing equations like this. And now we are starting to notice some details again. What is option 2? What type of function? Exponential.
I'm sorry.
So what makes an exponential function exponential? It has a what type of rate of change? Constant what?
Multiplication.
Because remember, here's a constant as well, right? So we need to recognize an exponential function is constant multiplication. Hey, because what operation shows repeated multiplication?
Exponents.
An exponent. There's a pattern there. There's a relationship there. And so we want to note that an exponential function has a constant multiplicative rate of change.
I've never heard that word.
No, that's just the adjective form of multiplication. Multiplication's a noun. Multiplicative is an adjective. And if you ever see someone write ROC like that, that's just rate of change. It's this weird thing where like learning is important and you want to be well-rounded and know things and be able to explain things well, and communication language is important. Okay? So exponential function, right? The rate of change is a constant multiplicative rate of change. If you see repeated multiplication, and I will point out, division is just the inverse of multiplication. So if you see repeated multiplication or repeated division, you're looking at an exponential function. Okay?
What is ROC?
Rate of change.
The lazy, this is.
Don't yell at me.
You don't see that, right?
I'm just hungry.
And by the way, does anyone know where we most easily see that multiplicative rate of change?
And the Y.
Yes, in the Y, but where did we see that? In a table.
Yeah.
And tabular representations are where you're going to see that rate of change most easily. Seen in tables. Alright? So we've already written an equation here. Alright? We wrote f of x equals 0.01 times 2 raised to the x. That 0.01, I already mentioned it, that was the what?
The pennies. I mean, yeah, right?
Not just the pennies, that was how many pennies he started off with, right? Remember that was when the day was 0. That's my y-intercept. You don't always start with a y-intercept, but in this form you do, which means that I need an input of what here? The y-intercept, the input is always,
The 0.
think about it, if you're looking at a y-axis, what's the x value everywhere on the y-axis?
1.
It's between -1 and 1, which is
Zero.
0.
Zero.
I literally agreed with you that it was 0, and I was trying to illustrate why it's 0, because it's in between -1 and 1. So the y-intercept, right? What was this 2 again? That was the rate of change, the multiplicative rate of change.
That's a word for it.
Yes, I like that word.
Okay? It's a constant multiplicative rate of change. And so, is every exponential function going to have that same y-intercept and that same
No.
rate of change? Okay, so the general form that you want for exponential functions are a times b raised to the x. Again, a is that y-intercept. This b here, the base, is your multiplicative rate of change. And the variable x is, or x is your input variable. Bless you. Worry about yourself. Okay. So the last representation that we have not addressed yet, what is it?
Linear.
Representation. Graphical. We'll talk about that in a second. But we have not addressed linear. So exponential, right, had a constant multiplicative rate of change. Remember that repeated multiplication is why I have an exponent, a variable exponent. when we're looking at the linear, what type of rate of change does it have? Constant, additive, which I will point out that means you could be adding or, yeah, right? So a linear function has a constant, additive. I notice none of y'all are freaking out about additive. Notice it's just the adding form of multiplicative.
Right?
Constant additive rate of change. Again, that is seen in tables most easily. What were you going to say?
What's subtract?
I would still call it additive.
What about dividing?
For subtraction?
Yeah, because if I take 5 minus 3, can't I rewrite that as 5 plus negative 3?
Division.
Subtraction is a type of addition, right? Notice 8 divided by 2, that's the same thing as 8 times 1/2. Division, again, is a type of multiplication. Okay? What does that fraction bar right there
It's
mean?
mind-boggling.
Division.
Divided by. That's why I always want you to think about it as division. 8 divided by 2 is the same thing as 8 times 1/2.
You had me lost when you said subtraction was addition, something like that.
Right here, subtraction can always be rewritten as addition. So instead of saying subtractive or whatever else, I don't know exactly how to say it, I would just say it's an additive. You're just adding by a negative. Okay, so linear function.
I ain't writing.
That's not the focus right here. This is the focus. That was just an example. Okay, so what was the equation that we came up with for how much money Killua is making with option 1?
60,000.
Okay, so there was a 60,000 in there. F of x equals. So if it was just x plus 60,000, x is the number of days. Are we just taking the number of days and adding 60,000 to it?
No, it's like 0 plus 60,000 every day.
0 plus 60,000 every day. Okay, let me ask you a question. How could I mathematically show that I'm repeatedly adding every single day?
Exponent.
No, that's multiplying.
So remember, an exponent is repeated multiplication. What's repeated addition? Multiplication. So 60,000 times x. If I take 60,000 and I multiply it by 30 days, do I get the 1,800,000 that he made? Yes. So if you go back to the core of what these things mean, it's not random. This isn't a random equation. Hey, I'm repeatedly adding, and repeated addition is multiplication. Now, we'll point this out. This is actually how I prefer to write my linear functions, the y-intercept, and then, does anyone know what this rate of change is called?
Addition.
It is repeated addition, it's constant additive, but there's an S word that we talked about earlier. Slope.
Yeah.
Traditionally, y'all are used to actually writing this equation as 60,000 times x plus the y-intercept of 0. What is that equation that I'm referring to? Y equals... That's what we're talking about when we say slope-intercept. Okay? And so, notice that this multiplication here exists because we're constantly what? Adding. Okay? Alright, we're starting to get there. So I just want y'all to notice, right? These equations are not random. There is meaning to these equations. So, this 60,000 and m, right? That's called the what again? That's the slope. Or that's the constant additive rate of change. That is one form of the equation. By the way, what is this b here then? That's the y-intercept this time. Okay? So we got our slope and we got our y-intercept. Those are our equations. Now I would assume we already know what a linear function looks like on a graph. What is it?
A line.
A line. So graphically, make sure you put a note here. It could either look like this, which would have what kind of slope? Positive, or it could look like that with a negative slope. Alright, so hey, hold on guys, we got 4 minutes of good learning. and I need y'all to see this. So what I'm actually about to do is called create a scatter plot, and what I'm going to use for the scatter plot, for the independent variable that inputs, what was on the table? What did we name that column? The independent. Days, right? I named it days, and what would it be for option 2? Option 2, okay? That's it. And this calculator graphs it for me. Notice if I type in that equation that we wrote, menu, graph entry, I'm going to go to function. Was it 0.01 times 2 raised to the x? You don't have to type this in, I just need you to see. That equation, does it perfectly match every single one of those points?
Yep.
Yes. So, I just need you to see quickly what the shape of an exponential function is. Notice, does it actually get to the x-axis?
No.
No. It's approaching it just like that standard normal distribution on the tails. It approaches, but it never actually touches. And then it's going to have what's called an exponential curve. Make sure you have a note about the shape of an exponential function there. It can also go in the opposite direction where it's called an exponential decrease out to the right. Okay?
See, I remember talking about it.
Okay. So, these are the things that are the basics of linear and exponential functions. Tomorrow we will get into quadratic functions, but you need to know these things. You need to hold on to your notes and use these as a study resource to know linear, exponential, and to know linear and exponential.
How do you put an X on it?
The little caret symbol next to where it says squared. Alright, so as a quick note, hold on. Okay, we do not have any daily practice assignments yet, because we're just starting to explore. But I do want to end with this. Hey guys, we still have over 60 seconds. Chill. Let me stop packing. Stop. I want to remind you, overall, I know some of us are still giving me deer in the headlight looks, but we're just getting into this for the first time. And I want you to understand, legitimately, for sure today, I feel like there's been some good learning today. But what are all of you? Still what?
Capable.
Not just capable. Capable of
Learning.
more.
Oh, man.
That's the one I want y'all to do. So, all together to end, and then you can pack. I feel like there's been some good learning today, but what are all of you?
Capable of
Capable of more. There we go. So go ahead and pack up. One person per group. Please put those calculators over there. Hey guys, make sure you go ahead and take each of your pages for all these lessons. And don't make me come after you. Hey, if you already know that you're struggling with any of this linear exponential,
That wasn't my finger.
go into tutoring.
Might have to call a certain number.
Yeah, regular days
Do
and
not
that right
leave
there.
something behind.
Register sex offender.
Oh, do you have them with you?
I ain't saying a bad word.
I'm gonna find it.
I told Salita she was a registered sex
But
offender.
like, okay, hold on a second.
Kiki.